Good morning, everyone. My name is Vincent. Today I'm talking about the bioluminescence imaging spectrum of four species: Parasoma atlanticum, Parasoma menacem, Euphorsia genera, and Godostoma. First is introduction. What is bioluminescence? You may never hear this word, but you may hear blue tears. It's blue light produced by algae in ocean. And you may ever hear tomato in movie Moana. It's a huge crab with a lot of different colors. So to put it simply, the bioluminescence is the light produced by a living creature. Just like this, a living creature. And we focus on the bioluminescence emission spectrum because it helps us to explain the function of marine bioluminescence. We can know the color by the bioluminescence emission spectrum. The color helps us to know the attenuation of light in seawater, and it affects the creature's perception of light. And this is very important to the relationship between the predators and prey and their mate. So in the ocean, we focus on the four species. First is Parasoma. Many colors have been reported before. So in this picture, we can see blue and red. And this is a colony of Parasoma. It means a group of Parasoma. In this study, each Parasoma sample is a group, just a colony of Parasoma. And this is a big colony, and this is a small colony. Next is Godostoma. It's a kind of fish can produce light in deep water. And this is a photophore. Okay, you can see here. It's the structure this fish produce light. And the last is Euphorsia. This is real Euphorsia. So what we want to do is we use bioluminescence imaging spectrum to know the structure and characteristic of the why this creature produce light, or they produce light to help their life. Methods: we get samples, use this research vessel Trident, and we use ISA kits, meltwater trough to get sample. When we get sample on boats, we just get fresh organisms and we put it into darkroom, and when we go back to the laboratory, the lighted organisms will put into a grating spectrum, the spectrometer. A grating spectrometer can help us to determine the wavelengths, and a part of two peaks more than 3.5 nanometer can be analyzed. Results. So what happened in these four species? First is Parasoma. We see these pictures before, and this is the result. In these pictures, the x-axis is wavelength in nanometer, and the y-axis is relative in density from 0 to 1. And this is a picture help us to know which wavelength means which color. And this is peak. We have one colony of Parasoma atlanticum, and the peak emission is around 492 nanometers. It's around blue and green, you can see here. And it's green than other species. Next is Parasoma menacem. We have three colonies of this species. So each data in here is mean. And the peak emission is around 485 nanometers. It's more blue than Parasoma atlanticum. Next is Godostoma. The spectrum obtained from a photophore, we mentioned photophore before, is the structure this fish produce light. And the peak emission is around 503 nanometers. It's longer than Parasoma. The next species is Euphorsia. and its peak emission is around 468 nanometer, and is the bluest spectrum in our study. You can see here is is the bluest, and this is special because we have narrow spectrum. And what does it mean? We will mention later. Before to go next, I want to introduce two words for you. First word is FWHM. It means full width of spectrum at half the maximum intensity. This width means so the value of this width is FWHM, and it means in the half of relative intensity, because in this spectrum we may not see every color it produced. It may produce many colors, but some color may be too weak, so we cannot see. And the FW10%N is similar to FWHM, but it's at 10% of maximum intensity here. So this table is the all data of our study. We have species, peak, FWHN, and FW10%N. And you can see we didn't have a FW10%N in some species because of the in the Perisoma atlanticum we don't have a 10% data in some relative density. Discussion. First, we find that Perisoma atlanticum produce blue light. Kemper and Bolden, they also find the peak emissions, first peak and second peak. But in our data, we only find one peak. We don't have a second peak, and we think it is instrumental artifact. It means it's just error because the second peak only appear in some special situation. So we think it's just an error. And these three studies have a same conclusion that these species, Perisoma atlanticum, produce blue light. Next, we focus on the changes in bioluminescence of Perisoma atlanticum. Birdhouse, they find that in some situations, the color of this species change from blue to red. In two situations, if it or it's decomposing. And why it changes its color? This is in general situation. This species produce blue light. But if it heated or decomposition, in outside, it will have a heated or decomposition catalyst outside. So the origin blue light produced, but when we go out, it will have a selective filtering, and the color change to red. So what is selective filtering? This is a light resource, and it produces different colors. If a selective filtering happens, after it will only have some colors, but not all. So in this case, we have 5 colors, but after selective filtering, we only have 2 colors. And in this situation, the FWHM value will change. In first, it's around 450 because almost every color it produced almost every color, so the value is large. But after it will be small. So if selective filtering happens, the FWHM will be small. Small value. And in the Gonostoma species, it probably Gonostoma elongatum, but the specimen was damaged, so we cannot sure. And probably find that the light organs have a direct connect to outside. So the photophore is inside the body, but it have a connecting to outside. So we can see the Gonostoma. The FWHM of this species is in relatively large group. So we have So we have a large value of FWH. It means the selective filtering did not happen. And the glioblastoma species, in this situation, we can see the emission spectra affected by overlying tissue very slightly. The last species is Euphausia. And also they find in low FWHM, it means filling by overlying tissue. And we can see Euphausia is in the small value of FWHM. So, because we have small value of WHM, the selective filtering is happened. So light from the photophore has been selective filtered. Conclusion. So, after all, the perisoma at the lens can produce blue light. We said that in the past it reported have many different colors, but in our study we say they only produce blue light. And what may change the color of perisoma? If it heated or decomposed, the select filtering will happen, so the color will change. And these two species is glioblastoma and Euphausia. And the FWHM value is large in glioblastoma and small in Euphausia. So the selective filtering will happen in glioblastoma but not happen in Euphausia. When we see the light produced by glioblastoma, it's just the color it produced in originally. But when we see Euphausia, the color we see is less than it produced. Thank you.